I will present about the electrical properties of laser-thin films fabricated by RF sputtering. I am Dong-Cheol in Department of ICT Automotive, Hosei University. AGO means the zinc oxide semiconductors doped with aluminum. Aluminum has a role on the conductivity control in the zinc oxide as an N-type dopant. The laser-thin film is one of good transparent conductive oxide materials. TCO means transparent conductive oxide, which is used for touch panel such as smartphone and tablet PC, or electrodes such as LED and solar cell. TCO is a very important material in the optoelectronic devices using light emission or absorption. Until now, tin doped zinc oxide (ITO) has been used as TCO. A smartphone uses ITO. Tablet PCs use ITO. LEDs use ITO too. If solar cells, the solar cell needs a vast amount of TCO. Therefore, another TCO material replaceable for TCO is necessary. The solar cells prefer AGO to ITO because it is cheaper and it has good electrical and optical properties simultaneously. This sheet is a few data about the electrical properties of laser-thin films reported somewhere before. For a long time, the research about AGO has been progressed and reported. There are so many data about the electrical properties of laser-thin films, but the results are confusing. In this work, we have a comprehensive study about the electrical properties in the laser-thin films fabricated by RF sputtering. Experimental conditions are like this. Laser-thin films are fabricated on soda-lime glass substrate by RF sputtering. Sputtering parameters are plasma power, working pressure, argon flow rate, and substrate temperature. The fabricated laser-thin films are thermally annealed under argon ambient in open tube furnace. Annealing temperature is room temperature to 500 degrees centigrade. First, I will show plasma power dependence. In the left figure, electrical resistivity in laser films increases with plasma power dependence, with the increase of plasma power. Electrical resistivity increases with the increase of plasma power. Electron concentration is vice versa. In the right figure, electrical resistivity decreases with the increase of annealing temperature until 400 degrees centigrade. Above 400 degrees centigrade, it has a tendency to increase. The electron concentration is vice versa. We can say that the increase of plasma power increases the sputter yield and deposition rate, which induces the carrier compensation of aluminum donors and donor-type defect by the increase of structural imperfections. Second, I will show working pressure dependence. In the left figure, electrical resistivity increases with working pressure. Electron concentration is vice versa. In the right figure, electrical resistivity decreases with the increase of annealing temperature until to about 300 degrees centigrade. Above 300 degrees centigrade, it has a tendency to increase. Electron concentration is vice versa. We can say that the increase of working pressure supplies insufficient film formation energy due to impingement between sputtered atoms and argon positive ion, which induces the carrier compensation of donor by increase of structural imperfection. Third, I will show argon flowrate dependence. In the left figure, electrical resistivity decreases with argon flow rate. Electron concentration is vice versa. In the right figure, electrical resistivity decreases with annealing temperature until 400 degrees centigrade. Above 400 degrees centigrade, it has a tendency to increase. Electron concentration is vice versa. We can say that the increasing argon flow rate is reported to decrease grain size and increase the number of oxygen vacancies in the age of thin films. The argon flow rate is a good choice for the conductivity control in the age of film. Fourth, I will show substrate temperature dependence. In the left figure, electrical resistivity decreases with the substrate temperature. Electron concentration is vice versa. In the right figure, electrical resistivity decreases with annealing temperature until 300 or 400 degrees centigrade. Above it, electrical resistivity has a tendency to increase. Electron concentration is vice versa. We can say that the increase of substrate temperature increase the energy necessary for the formation of a aluminum zinc oxide bond, which reduce the formation of structural imperfection and suppress the carrier compensation of aluminum donor or donor type defect. Finally, I will show the relationship of electron concentration and electron mobility in the age of thin films. Y-axis is electron mobility. X-axis is electron concentration. Electron mobility is proportional to electron concentration. Age-thin films of higher electron concentration have higher electron mobility. This is the opposite result to the general electron scattering mechanism. This is the opposite result. We can say that the electrical properties in the age of films is determined by serious or less serious carrier compensation due to the formation or annihilation of a conductive defect, such as structural imperfection of aluminum donor, or donor type defect and grain boundaries. Let me conclude this presentation. We offered extensive data about electrical properties of age-thin films on glass substrates fabricated by RF sputtering. Electrical properties is like this. Electrical resistivity is proportional to plasma power and working pressure. But electrical resistivity is inverse proportional to argon flow rate and substrate temperature. Electrical resistivity decreased with annealing temperature until a critical temperature, and after that electrical resistivity increased. The critical temperature is about 200 to 400 degrees centigrade. Electron concentration is vice versa. Age of films of high electron concentration had high electron mobility. It was suggested that electrical properties of the age-thin films is determined by a serious carrier compensation or less serious carrier compensation due to formation or annihilation of conductive defect, like structural imperfection of aluminum donor type defect, and grain boundaries. This work was supported by Korea Institute for Advancement of Technology, KIAT, grant funded by the Korea government. Project number 1015132, Hydrogen and Eco-Friendly Energy Open Net Project in Chungnam. Thank you very much.